as a choice. Let's take a look at a second case study. Involves a fan that's used for vacuum cleaners. And here is an example of what that looks like. And let's say we are trying to make it out of a thermoplastic. Nylon is an example that's commonly used, maybe glass reinforced. Um, the shape is solid, 3D, just like in the previous case. Right? But now the only difference is instead of a non-ferrous alloy, you have a nylon that is a thermoplastic that's in consideration. You have some mass constraints and other dimensional issues and batch size. So of course, you know off the top of your head that an injection molding solution might work just as well. But let's go through this type of an exercise in terms of how that, knowing what to anticipate, let's probe to see how reliably and how effectively Granter would navigate through the hundreds of options that exist for the tens of thousands of materials and a dozen odd different shape variants to arrive to that final conclusion, and especially from the perspective of minimizing cost. In addition, you can also get some quantitative comparisons between different processing techniques in terms of trade-offs. Here again, the free variables are which process can we use and specific operating conditions in terms of the time, temperature, pressure combinations that govern the fabrication of a shape from any processing technique with a given material. So nylon, a thermoplastic, you can go into the database and see what all they could be used for and kind of break into this kind of a pie chart, right? A lot of automotive related applications, some electrical and domestic appliances. So somewhere in this category for the domestic appliance is where we see nylons commonly used. And then of course after that it breaks into a bunch of different other options. Okay. So just in terms of looking at nylon, and within nylon itself there are a range of molecular weights, a range of chemistries, and a range of fillers that govern specific attributes in terms of density, cost, operating temperatures, so on. Right? And there are some variants that can be cast as well. So now if we go ahead and look at this familiar matrix where you have a row of processes and a row of metals, right? We again go through that familiar recognition that certain processes work better with certain kinds of materials, and the thermoplastic family, now we are going to the lower half of the table as opposed to the top half that we considered previously for the non-ferrous materials. Again, then we walk from there into the shape-related restrictions. And for thermoplastics, for instance, here are some kinds of examples compared to the last case for the non-ferrous alloys in terms of what is possible for creating 3D solid objects. And if you look into the process shape combination, where shape is the columns and processes remain the rows, you come across the possibility that here we have certain options for the 3D solid filter out among this lower half over here. And largely what stands out is some form of injection molding, as we suspected, compression molding, which, for a thermoplastic is surprising, but what does that mean? And resin transfer molding, right? So these are some things that stand out. In terms of size capabilities, again, as it turns out, injection molding works great. And some of these other things, are you familiar with what rotational molding is? Something to look into. If not, then you can explore that in the process universe in terms of details. Yes, during ME 381 went through a wide range of these processes, and it was boring because it's a lot of detail. It still does not get you to pay attention to when do you select or prescribe a vendor for what design occasion. That is where building off from knowing what processes are out there and then going down to specifically which ones work for your specific design, product design issue, and how do you arrive at options is a crucial thing to consider. Here's on a mass basis. The second aspect is in terms of following the mass is based on the section thickness in a similar manner that we saw earlier. And again, injection molding and is in the running, as is compression molding and a couple of others. In terms of tolerances itself, injection molding is right there in that sweet spot. Roughness, similarly, because we're using a highly polished die, you can get to very low roughnesses. And you have a rotating part that's spinning around for the fan, for the vacuum machine. So being able to have that precision is very important in this particular case. Most of the processes that are polymer based will satisfy uh, those constraints. Batch size now becomes an important issue, and we are looking at, again, let's say 100,000 pieces. You begin to see that many of the options fall off, including polymer casting, and you're basically stuck with a couple of options for the specific shape and in terms of the injection molding and compression molding. And the top half looks at some variations in terms of what is required in terms of then the die design relative to the part design and the injection molding conditions for being able to make defect-free parts, high-yield parts, and how to address cost-related issues between this option over here or go to a compression molding variation depending upon the chemistry and the shape-related attributes.